channel. Dear students, today in chemistry we will be in a phase equilibrium, talk about phase diagram of another two component system, that is Na and K system. Before we start our today's topic, let's take quick recap to our previous lecture. What we discussed in our previous lecture, that is Mg and Zn system. A substance is said to be possess a congruent melting point if the melt is completely into liquid phase having same composition. As you know, that is called congruent melting point system. There is a 4 phases available: solid magnesium, solid zinc, the intermediate of Mg and Zn twice, and solution of zinc and magnesium. There are also 4 curves available: curve AC, this is called freezing curve of zinc; curve DE, that is called freezing curve of magnesium; curve DC, this is called melting curve of intermediate of Mg and Zn twice; and curve DE, this is called melting curve of Mg and Zn twice also, right? So for that is a degree of freedom is 1, therefore the system is bivariant. There is also eutectic points available. In the first eutectic point of the system where 3 phases, solid zinc, solid Mg and Zn twice, and solution are in the equilibrium. So degree of freedom is 0. So it is a non-variant point, right? In eutectic point E, it is a second eutectic point of the system where 3 phases, solid magnesium, solid Mg Zn twice, and solution are in the equilibrium, right? And another one is eutectic point D, is a melting curve of solid Mg and Zn twice, right? Area also available above the curve. ACDEB system is liquid mixture of zinc and magnesium, as it is one phase, right? So now today we gonna start incongruent melting point system, that is called Na and K. So you have to know about what is incongruent melting point. So when system is said to possess incongruent melting point if on a heating it decomposes at a temperature much below its melting point. What on heating? I will write down here. On a heating, it decomposes at a temperature much below its melting point, much below its melting point, right? So this is called incongruent melting point, and it's form a new solid phase, and it form a new solid phase, and this liquid state has a different composition from that of the original solid state, right? And composition was a difference, so that is called incongruent melting point, right? So in incongruent melting point, N and K system is a 2 component system having incongruent melting point, and melting point of sodium and potassium are melting point of Na and K are 98.8 degrees Celsius and 63.8 degrees Celsius, right? Now both elements chemically combine together chemically combine together in the ratio that is 2:1 to form a compound, intermediate compound. What is that compound? Na twice K, right? But this compound is unstable and decompose into solid Na and melt at 70 degrees Celsius temperature. But this compound is unstable and decompose into solid Na and melt at a 70 degrees Celsius temperature. It is incongruent melting point or peritactic temperature of the system. It is called incongruent melting point, or you can say also peritactic temperature of the system, right? So you can know about this, and it has a 4 phases. System consists of 4 phases, right? Which one 4? First one is solid Na, another one is solid K, third one is solid Na2K, this is an intermediate, and fourth one is liquid of Na and K, right? Pressure doesn't affect this type of system. Most important point, pressure doesn't affect this type of system. So reduced phase rule applicable on Na and K. Here reduced phase rule applicable. What is reduced phase rule? F dash is equal to C minus P plus 1. This is reduced phase rule, and F is equal to C minus P plus 2. That is only phase rule, right? So here there is a basic information related to our topic. Now let's look at figure. So here I'm gonna draw a figure of Na and K system. In x-axis we can take a composition. Here we can take composition, and here we can take temperature, right? Temperature. So now we can draw here line. This is that's, and also we can draw here also line. So that is look like this way, right? So now we're gonna be draw curve. This is curve, one curve, another one is this, and another one is this. So here I'm gonna take this. So this is a look like this system, right? So here we point out here point A, point C, here point D, and here point B, right? In the left side we can take 100% potassium, 100% potassium, and Na is 0%. In the right side Na 100% and K 0%, right? So here we're gonna take K, and here, we can draw here line. Here we're gonna take an A, and here melt, right? Here also the solid K present plus solid Na2 and K, and here also solid Na present plus solid Na2 K. In here also solid K, this is a solid form, plus liquid melt. Here also Na solid plus melt, right? So here temperature is 63. So here also temperature 63.8, and here 97.8, 97.8 degree Celsius, right? Now this is a point called eutectic point. Eutectic point, here minus 12 degree Celsius, right? We can also take a name here. We're gonna J, F, G, K, L, and H, right? So this is your figure. And now we're gonna discuss about curve. Curve, right? First of all, curve AC. Curve AC means this curve, A and C, right? It is known as a freezing curve of potassium. Here 100% potassium available, right? But now we can add gradually in Na. Now we here add Na gradually, that means slowly. So the melting point of curve potassium is decreases slowly. It will be decrease slowly if we add Na in this potassium, right? So it is known as a freezing point curve of potassium, or you can say melting curve of potassium, right? So curve AC is known as a freezing point of K, and this curve shows the lowering in a freezing point of potassium. So this curve of K showing the lowering in freezing point of K by addition of Na and continues till the point C is reached. અહીંયા સુધી એડ કરવાનું, right? And continue till the point C is reached, right? So separate out a solid phase at a new and a new phase Na2K we get, right, at point C, and two phases solid K and liquid melt exist in equilibrium along with this curve, right? So now curve CD, this is called curve CD, curve CD. It is known as a fusion curve of Na2K. It is called fusion curve of Na2K. Here at that point only Na2K can exist, and this is called fusion curve of Na2K. And two phases, which one? Solid Na2K and liquid melt exist, right? Exist along this curve. If compound would be stable as having congruent melting point, then the curve may be plotted up to the stable melting point E of the Na2K. Now curve BD. Write this curve BD. This one, right? B and D. It is known as a fusion curve of sodium. It is called fusion curve of sodium, and this curve shows the lowering of freezing point of sodium by addition of potassium. So here only Na is present, right, at the point B. If we add K, so its freezing point is gradually decreases at point D, right? So we can write down the curve shows lowering in freezing point of sodium by addition of K, right? So K. Continue till the D point reach. And along the curve, sodium separated out as a solid phase, and this curve, a new phase Na2K separate out at a point D, and two phases solid Na and melt are the equilibrium of this. Now what is the degree of freedom? F. What is the F for AC, CD and BD, right? So here we can apply reduced phase rule, C minus P plus 1. So is a two component system, that is C is equal to 2 minus, in this curve AC, curve CD and curve BD, two phases available. In curve AC we can see solid K present and liquid melt present. In a curve CD also present the new component intermediate Na2K twice, and also melt is present. In curve BD also solid form of Na present and melt. So here in all phases, in the whole curve two phases is present. So here 2 plus 1. So F dash is equal to 1. So that is, this is univariant. So this is univariant system, right? So now we move on for a point. So now point A and B, point A and B, this point A and point B, right? Point A represent melting point of potassium and point B represent melting point of sodium. point A represent melting point of K, that is 63.8 degrees Celsius, and point B represent melting point of Na, that is 97.8 degrees Celsius. This is point B and this is point A, right? At both the point, two phases are in equilibrium at point A, but the point two phases are equilibrium. At point A, which one is present? Solid K and liquid K. Liquid K. Point B, solid Na and liquid Na, right? You can see. But both the point, so degree of freedom, F dash is equal to C minus P plus 1. Here two component system. Sorry, here one we can take a one component system, 1 minus 2 plus 1, so that is 0, right? At a point A and B, degree of freedom is non-variant. Now point C. Point C, this is called a eutectic point. Eutectic point. At that point, three phases: solid K plus solid Na2K and melt exist together, right? So P is equal to 3 and C is equal to 2. So F dash is equal to C minus P plus 1. 2 minus 3 plus 1. This is also 0. So this is non-variant system. But at point D, this is point D, this is called incongruent melting point, right? Incongruent melting point. This is called incongruent melting point. At point D, I'm going to fold this so you can see. At point D, point D occurs Na and K system at Na and K system at 70 degrees Celsius, right? So hence three phases: solid Na2K, solid Na and melt exist. So F dash is equal to C minus P plus 1. So 2 minus 3 plus 1, this is called 0. This is called non-variant, right? Now we're gonna discuss about areas, right? So area above ACDB. A C, D, B, area above, right? So only melt is present. Only melt is present. Melt. So F dash is equal to C minus P plus 1. So it is 2. So this is called a bivariant system. Now another area is ACF. AC and F. This area ACF. Only two phase available. Two phase. Which one? Solid K and which one? Liquid melt. Liquid melt, right? This area AC and F. Another one is EC and G, right? You can see where we EC, it's E, we write here E, C and G, right? E, C and G. So here we are gonna take E, right? So you can see E, C and G, this area. So two phases, solid Na2K and liquid melt is present. Solid Na twice K and liquid melt. Now area BDH. You can say B, D and H. B, D, H. So only solid Na and melt present. Solid Na and liquid melt is present. Now area below FCG. FCG, area below, right? Below F, C and G. Solid K and solid Na2K is present here. Solid K and solid Na2K present. Now area IHLK. IHLK. We're gonna put I, so you can write down, right? We can take HEGK, right? HEGK. So this is also from Na plus solid Na2K is present. But all area, so what is the degree of freedom? For all area, F dash is equal to C minus P plus 1. So here two component system, for all area, two phases available, right? So minus 2 plus 1. So F dash is equal to 1. So the area is a univariant system, right? So here all about your system Na&K system, and here your phase equilibrium, your chapter number 7 is complete, right? So if you have any doubts, then we will be arrange a Google meeting, so you can ask at that time if you have any doubts about this chapter particularly, right? Thank you.